Hi everyone. The topic of my presentation is point of interest oriented question answering with joint inference of semantic matching and distance correlation. Today's presentation can be divided into the following parts. First of all, I would like to introduce the task. Point of interest is a dedicated geographic entity on an online map where someone may find useful information, like a restaurant, a hotel, or a travel spot. POI has two important properties, which are text and location. Text refers to a short text in a POI describing its service, types, and so on. In addition, each POI has three location properties named as location entities, recording the POI located city, district, and area of interest. Below is a table containing some examples of POI. We can see that, for example, the first POI contains some tasks like name, type, major users, and three locations, which are New York, Manhattan, and Liberty Island. POI-oriented question answering problem is a special QA task which aims to answer users' questions by generating a list of POIs. With the rapid development of smart agents and intelligent virtual assistants, there are many POI-oriented queries being requested every day. Some examples of these questions are, where can I take my kid to have fun nearby New York City? Or where can we go in LA with my friends? The answers are typically a list of POIs. In this example, the answers are 4 POIs: New York City Fire Museum, Children's Museum of the Arts, Statue of Liberty, and One World Observatory. Traditional template matching methods convert the question to formal representations using predefined rules and are very simple and have a high precision. However, the form of the queries are always varies from person to person. Simply doing query matching lacks of flexibility. Based only on text, they always fail to analyze distance correlation. Machine learning-based QA models calculate the similarity scores between queries and the POIs. Nevertheless, they cannot work well in this task, since it is ineffective for them to handle the unique properties of POIs, such as tags and location entities. The major contributions of our model lies in 4 aspects. First of all, we tackle the POI-oriented QA problem by proposing a new deep learning model with joint inference. We leverage 2 neural network models to build a bridge between questions and POIs on both POI tags and question location terms. We also adopt a skewed distribution method to deal with proximity-related terms. We design a special embedding structure using cross-attention mechanism to obtain a more precise and flexible representation of questions. And we conduct comprehensive experiments on 2 real-world datasets, enabling the evaluation of the results from different perspectives. Experiment results demonstrate significant improvements of PJI over all the state-of-the-art baselines. So, the graphic shows the overall structure of our model. Generally, our model is made up of 2 parts, namely text semantic module PT and distance correlation module PD. The model takes question POI pair as input and the probability of choosing a POI given the question as output. Given question QJ, the probability of choosing POI AI, denoted as PAIQJ, can be estimated as maximizing the log likelihood of the sum of 2 parts. PT is the partial probability of choosing POI AI given question QJ in text semantic module. YA is a tag, and VT refers to the tag set. PD is the partial probability of choosing POI AI given question QJ in distance correlation module. YL is a location entity and VD refers to the location entity set. According to the formula mentioned above, the probability of choosing a POI in tag semantic module can be denoted as follows. So the probability that question Q contains tag YA is as follows. And we take the softmax output of WY times FENTQ. FENTQ is word embedding of Q, and WY is the parameter we would like to optimize. The probability that POI AI is chosen given tag YA and question Q is formulated as follows. Here, FPRQ is a cross-attention based word embedding of Q, GAI is the embedding of POI AI, and epsilon is a direct delta function. For POIs with YA, the function is set to 1, otherwise the function is set to 0. This picture shows the cross-attention mechanism in the question embedding. The mechanism contains two parts, A to Q attention model and Q to A attention model. The former one embeds the question according to different tags of POI, forming one embedding for each tag, and the later one learns the weights corresponding to the vectors obtained from the last step. Another module is called the distance correlation module. As for PYL given QJ, we directly extract location entity from question using NER tools. For example, we extract New York from the question, where can kids go in New York? As for P, AI given YL and QJ, it has a relationship with the distance to the location entity, indicator function, as well as the area of location entity. In detail, we calculate the sigmoid output of the linear transformation of the skewed distribution. Here, F is a skewed distribution. If the question does not have proximity-related term, tau equals to 1, otherwise tau equals to -1. Proximity-related terms refer to terms like nearby or close to. Figure 3 shows the POI probability distribution concerning distance. X-axis is a log distance between the POI and the location entity polygon. If POI is outside the polygon, the distance is positive. Otherwise, it is negative. Y-axis is the probability the POI is recommended. PRT denotes proximity-related terms. In 3A, we can see that for questions without PRT, we mainly retrieve POIs inside the polygon, while for questions with PRT, we mainly retrieve POIs near the polygon border. In 3B, we can see that when asking city-level questions with PRT, for example, where can children go nearby New York, the result may contain POIs located in city suburban district or outside the city, whereas for AOI level questions, for example, where can children go nearby Central Park, the result may only contain POIs outside but close to the border of AOI. This is because the area of a city is much bigger than that of an AOI, with different area size of the location entity. The probability distribution functions are quite different. Next, we would like to talk about the experiments. The table records the overall performance over two datasets. Dataset A contains POI-related questions whose geographic entities are located in Beijing. In dataset B, the location of the questions is not restricted in Beijing, but in China. The first two methods in the table are the semantic parsing methods, and the remaining ones are neural network-based models. From the table, we can see, compared with typical neural network-based models, semantic parsing-based models have a higher hit at K rate on the whole. And in general, models with attention mechanism reach better performance than models without. Our model achieves best performance among all the models. Table 2 shows the hits at 5 rate on questions containing different location entities. And from the table, we can see that city-level questions obtain the best results compared to other two types. This is because the number of cities in the whole nation is rather small, and the location entity is hierarchical. This table shows the hits at 5 rate concerning questions with and without PRT on 2 datasets. And from the table, we can see that all existing baselines cannot handle questions with PRT. However, this problem gets tackled by the distance correlation module in our model. Here are some examples of the retrieved results of our model. The question means, where can children go nearby Guangzhou? And as mentioned before, it is a question with PRT. The retrieved results are mainly located in the suburban areas of Guangzhou and some cities close to Guangzhou. In this example, the question means the places for kids to go in Zhangjiakou. Since the question does not contain PRT, the retrieved results are all located in Zhangjiakou. So, in conclusion, in this paper, we propose a deep learning framework with joint inference to solve the POI-oriented question mastering task. Our main contributions lies in 3 aspects. First, this model handles the POI-oriented QA with the help of text semantic module and distance correlation module. Second, by introducing a cross-attention-based question embedding structure, we achieve a precise and flexible representation of questions. Third, the proposed model can overcome several challenges of POI-oriented QA, including POI tag recognition, proximity-related term processing, and diverse distance correlation. Extensive experiments on 2 real-world datasets are carried out to demonstrate the effectiveness of our model. The result shows that our approach outperforms all the baselines and state-of-the-art models. That's all for today's presentation. Thank you.